Today we are very happy to have Peter Jossen of ETH Zürich, and he's going to speak about exponential motives and their fundamental groups.
Thank you. Thank you for the invitation. Now, let me, okay, I'm completely off. Sorry, small technical problem. I'll get this fixed in a second. All right, let's try this again. Okay, can you see the title?
Yes.
Yes.
All right, okay, good. Again, thank you for the invitation. And great pleasure to talk in Toronto. I don't have any jet lag whatsoever, so that's fine. My talk will be today about a theory of exponential motives and about the computation in a few examples of their tannakian fundamental group. The whole work is joined with Javier Frezan, and we have a book in preparation about the subject. You can find this best on Javier's website because he's updating this more diligently than I am. All right, so for the whole talk, let me fix a number field inside the complex numbers, and let's just agree that variety throughout the next hour means a reduced K scheme of finite type. So all varieties are varieties over K, and they don't need to be irreducible. So something that is certainly well known is that if you start with a variety X and some closed subvariety Y, you can get out of this a pair of topological spaces just by looking at the complex points of X and inside them the complex points of Y. So these are nice topological spaces. They have the homotopy type of finite CW complexes. And once you have a pair of topological spaces, you can look at singular cohomology of the pair. So that will be singular homology of the pair with Q coefficients, and it will be a finite dimensional Q vector space. And so this is singular cohomology, and I will just to ease the notation not always write complex points. So Hn xy is a singular cohomology of the pair of spaces of complex points. And this singular cohomology, it's really a good cohomology theory in the sense that it's functorial in the pair. It satisfies Kunet formula for products, and there is a bunch of long exact sequences like the Mayer-Vietory sequence or the long exact sequence of triples when you have Z contained in Y contained in X. So it's reasonable to call this a kind of nice cohomology theory. And what I want to do now is I want to enrich this situation to the setup where together with the variety X and maybe the closed subvariety Y, I am given on top a regular function on X. And now I will associate with triples X, Y, and the regular function a number of cohomology theories. So what should substitute now the pair of spaces? Well, I'm going to look at inside the complex points of X, the complex points of Y, union those points of X where the real part of the function is larger than some real number R. And think of R as a big number. So this is still a pair of topological spaces, and I can look at the cohomology of this pair. It depends on R a priori. So the singular cohomology of this pair is some nice vector space, and it depends on R. And since I don't want it to depend on R, I'm taking the limit as R goes to infinity. So that's a colimit. Here it's with respect to the obvious inclusions when you take R larger and larger. It's still a finite dimensional vector space. This colimit, it stabilizes as soon as R is large enough. And that's what we call the rapid decay cohomology of the triple XYF. So the name is now rapid decay cohomology. When the function f is 0, you get just ordinary singular cohomology of the pair. But still, even with the function, you now have a cohomology theory, which is functorial in the pair for the obvious type of morphisms that you want to look at, which are compatible with the given functions. There's a Kunet formula, and there is a bunch of long exact sequences associated with it. So that's maybe the easiest cohomology theory that you can associate with functions on a variety.
So Peter, at the moment, f has nothing to do with y, right?
F has nothing to do with y and will never have to do anything with y. Let's look at the example here. So for my variety, I'm taking the affine line. The subspace y, I'm taking it empty, and so a regular function on the affine line is just a polynomial. So let's choose one of degree 4 with a monic dominant term. So inside the complex plane, we are looking now at the complex plane. We are looking now at those points where the real part of the polynomial f is large. So since it's of degree 4 and has a leading coefficient 1, there will be 4 regions where the real part of f is very large. Namely, when x is some positive number, or vaguely a positive real number, or vaguely a negative real number, but also when x is somewhere up or down on the imaginary axis, x to the power 4 will be a large real number. And the lower order terms don't interfere too much with this. So the region f of x, real part, is larger than R. When R is large enough, is 4 simply connected regions in the complex plane. And so the rapid decay cohomology of x and f would be the rapid decay cohomology of this pair. And at least in homology, you can represent the cycles by paths that go from one of these regions into another. So here we see 3 paths that go from one region to another. And these 3 paths, they represent a basis now not for the cohomology, but for the homology. And the dual space would be rapid decay cohomology. You see that the last one, so that the path that goes from one region into itself, I don't have to add it because it's 0 homologically. So 4 marked points or 4 marked regions will mean cohomology of dimension 3. So it's the space is q to the power 3, and generators are here. Okay, so that's one sort of cohomology that you can have. Here is another one. Again, I'm starting with a variety x, some closed subvariety, and a regular function. But to show it, or to explain how this cohomology works, I'm going to assume, just for simplicity, that x is smooth and affine and y is empty. So if we have this, we can look at the complex of differential forms on the variety x. So omega 0, these are the 0 forms. So if x is spec of A, then omega 0 is just the algebra A. And then omega 1 are the differential 1 forms. Omega 2 are the differential 2 forms, and so on. And these spaces of differential forms, they form a complex with the exterior derivative. But I'm not going to look now at the normal standard derivative. I will change the differential. I will twist it using the function f. So instead of just going with the operator d from omega I to omega I plus 1, I will use the operator df, which sends omega to d omega plus df wedge omega. So that's a modification of the differential in the classical de Rham complex. You can check that it's still a differential, so df composed with df is 0, and we define the RAM cohomology of the pair xf just as the cohomology of this complex. Again, notice that if f is 0, you get the ordinary de Rham complex for x. And now you will have to trust me that this definition, which I gave you just for smooth and affine x and y is empty, this has a natural extension to the case for any x and any y. So it's called the Rham cohomology. And again, it's a nice cohomology theory in the sense that it's factorial. There's a Kunet formula, and there are all the necessary long exact sequences that you can wish for. All right. Also, let's see this one at the example. I'm just taking the same one. So x is the affine line, y is empty, f is a polynomial of degree 4. Now, the affine line, I'm writing it as spec kx. So x is the coordinate on A1. And then the de Rham complex it's very short. So there's omega 0, which is the ring of regular functions, kx, and there's an omega 1, which is kx dx, and that's the end of the de Rham complex, because the affine line is just one-dimensional and there is no non-zero two forms. The differential, so the only interesting map is the one that sends 1 to f prime x dx, or 1 gets sent to df. That's the differential, and you can see this differential map here. It's injective, and its co-kernel is generated by the forms dx, x dx, and x squared dx. So there's a little exercise in linear algebra that shows that this co-kernel is three-dimensional, and these three forms represent all classes in the co-kernel. So this co-kernel is the H1 de Rham of xf. And so you see, it's three-dimensional, just as before with our singular or rapid decay cohomology. It was also three-dimensional. And you might ask whether this is now a coincidence. And of course it is not. So there is a comparison theorem between the rapid decay and the de Rham cohomology, which, well, among other things, implies that the dimensions of the two cohomology theories, the Betti numbers, are the same. So here is how this goes. This comparison is called the period isomorphism. And it's an isomorphism between the rapid decay cohomology tensor the complex numbers to the de Rham cohomology tensor the complex numbers. Because you see, rapid decay cohomology is a Q vector space, and the de Rham cohomology is a K vector space. So you cannot, I mean, you're comparing apples and bananas here. So in order to put this on a common denominator, just tensor both sides with C. And then what I say is that there is a natural isomorphism between the two, which implies, of course, the equality of dimensions. So this map, this isomorphism, is best presented as a pairing. So I'm switching now from rapid decay cohomology to homology, and instead of writing the linear map, I'm writing a pairing. So that's exactly the same by linear algebra. So I want a complex valued pairing between rapid decay homology and the Rham cohomology. So in homology, I'm giving a cycle, that's a topological n cycle. And in the Rham cohomology, I'm giving you a differential form representing a de Rham class. And so what can you do with a cycle and a form? Well, you can pair them together by integrating. And now comes the twist here. We are not integrating stupidly omega over t, but we are integrating exponential of minus f times omega over t. So first, that's what you have to do if you want this pairing to be well defined. And in particular, that's what you have to do in order to make the integral converge in the first place. Why is that? Because you see the cycle t, it goes out to infinity exactly in those directions where the real part of f is large. But when the real part of f is very large, and we are integrating exponential of minus f times the differential form omega, the exponential minus f will decay very rapidly, much faster than the differential form, which is polynomial, has a chance to grow. So the fact that t is a rapid decay cycle means that exponential minus f in this integral decays rapidly, and that's where the name comes from. And so that makes the integral well defined. It gives you an absolutely converging improper integral, and this is how we make our pairing up here. The pairing is called the period pairing, and the real hard theorem here is now that this theorem is non-degenerate, and therefore indeed gives you an isomorphism such as claimed. So if you want to read about this, other than the book, I will stop now making publicity for it. There is an article by Marco Hin and Kahol Hukayahol in 2008. You just Google integral representations ... and you will find it. So this is the period isomorphism, and of course I want to check it also on my example. So again, affine line polynomial of degree 4 monic. Here is my basis for the rapid decay homologies. These are these paths that go from various directions at infinity to the real infinity. I have my differential forms, basis of the Dirac cohomology. So these are x to the, I'm writing it now as x to the k minus 1 for k 1 to 3. And I can now pair these together. So the recipe is a pairing of the topological cycle Tj with the form omega k is the integral over Tj x minus f. So f is this polynomial of degree 4 omega k. Or if I write this out, it's the integral, say, from minus infinity to plus infinity, or from plus minus I infinity of exponential minus x to the 4 minus tralala x to the k dx. And you see these integrals, when you think of it maybe from minus to plus infinity, this integral converges absolutely because the exponential wins over the function x to the power k. And even if I had chosen some other Dirac basis, maybe x to 1 million and x to 1 million and 1 and x 1 million and 2, still the exponential would win. And so it's really well defined here. To actually compute these integrals, it's pretty hard. So you get 3 by 3 integrals, so 3 cycles that you can integrate over 3 different forms. It gives you a 3 by 3 matrix that represents the integral, the period pairing. So to compute the coefficients of this matrix is, well, I would say impossible in the sense that these coefficients don't have any closed expression in terms of elementary functions. But just to see it, what comes out, let's pretend the polynomial is just x to the power 4 and no lower order terms. So then you have here a bunch of very concrete integrals. And once you make a change of variable and you call y x to the 4, you will see in these integrals essentially the definition of the gamma function. So indeed, up to a little noise, the value of these integrals is a special value of the gamma function at k over 4. K is the power of x in the differential form. And so the whole matrix, the whole period matrix, is the 3 by 3 matrix of, so with indices j and k of these integrals. It looks like this. And now if you find this funny, you can check that the determinant is non-zero and the pairing in this case is indeed non-degenerate. So you can check this on an example. Good. This matrix is called the period matrix. And you can already see now the numbers that come out in these period matrices. They are quite interesting. Good. I want one more cohomology theory, and this one will be technically a bit more complicated. The technicality is the kind of the target category where this cohomology lands in. And so this target category where the theory takes its values is a category of perverse sheaves on the affine line with vanishing cohomology. You call it perv 0. So 0 for vanishing cohomology. Sounds scary, but it's actually not that a difficult thing. So let me give you some feeling for what this category is. Objects, you can think of them just as actual sheaves. So you choose a finite set of complex numbers, and then you pick a sheaf of finite dimensional Q vector spaces on the topological space C, and this sheaf has to be locally constant outside the finite set S. And then, the cohomology of such a sheaf can be computed, and you have to choose your data in such a way that the sheaf has no global sections and that the H1 of the sheaf is 0. And that's actually enough, so there's no other cohomology group. So that's essentially pure linear algebra data, and an object of perv 0 is just that and nothing else. Well, the actual perverse sheaf is then not the sheaf F, but the sheaf F shifted to degree -1. So think of it as a complex of sheaves. You want to put it in degree -1. Morphisms are just morphisms of sheaves. And that's the category perv 0. So it's a special type of sheaf on the complex line. And that's all I want to say about these perverse sheaves as an abelian category. But there is one more feature. It is in fact a tannakian category. So these perverse sheaves, there is not just the direct sums and kernels and co-kernels and whatnot, but there's actually also a tensor product on this category of perverse sheaves. But it's not the usual tensor product of sheaves. It's not the pointwise tensor product. The tensor product works as follows. So if you have two such sheaves, say F and G, you pull them back to the affine plane by projections. On the affine plane, you take the ordinary tensor product, and then you push the result forward by the summation map back to A1. And then so you get some other new sheaf on A1, and it happens to be, again, an object of perv 0. And this procedure is called additive convolution. So what I say here is that perverse sheaves together with additive convolution as a tensor product form a tannakian category. There's a neutral object. It is the constant sheaf on the complex plane, except where we have killed the stalk at 0. So you take the constant sheaf, restrict it to the plane -0 and extend it by 0 back. So that's the neutral object. And there's a fiber functor which takes a perverse sheaf, write it as sheaf shift 1, and then what you do is you take the colimit of the sections of the sheaf on the open half plane real part larger than Z. And you see here a little bit resurface already the definition of rapid decay cohomology. So this fiber functor, it also has a name. It's called the nearby cycles functor at infinity. And that's a standard thing to do with perverse sheaves. Okay, so this category perv 0 is my target for a new cohomology theory for varieties x, y, and the function f. So let me construct this. So the first thing, I'm giving a name to the inclusion of the open complement of y into x. And I start fabricating a sheaf on x, which is the following. So I'm taking the constant sheaf on x, and I'm deleting, putting to 0, putting down all the stalks at y. So it's the sheaf which is constant on x, except on y, where there it is 0. So once I have this sheaf on x, I'm pushing it forward with the function f to the affine line. So f lower star, nth higher direct image of this on the affine line. And the little p here stands for the perverse T structure. So I'm taking the higher direct image, but not for the ordinary T structure, but for the perverse one. So it gives you a perverse sheaf on the affine line. It might have cohomology, so it's not an object of perv 0 yet, but next thing I do is we make the additive convolution with the sheaf E0. And now it's an object of perv 0. And this is what we call the nth perverse cohomology of X, Y, and F. Now, if you cannot see anything in this formula, no blame to you. So it looks a bit messy. Here is morally what this thing does. So what I have written here is a little bit in quotation marks, the sheaf on the affine line whose fiber at the point is the cohomology of the pair X and Y union the pre-image under F of the point. So when you move the point Z, this pre-image F inverse of Z will change, maybe sometimes drastically, but most of the time just a little bit. And you get some family of vector spaces, H and X relative to Y union F inverse of Z. And this family of vector spaces, that's the sheaf I'm talking about. The quotation mark is there because it's not actually true for all points Z, but only for those Z which are non-singular for the map F. So outside the critical values of F, this is true. So this just to say it's not that a complicated object, and we can compute its dimension, its monodromy most of the time just by looking at elementary cohomology of pairs. Good. There's a comparison between the perverse and the rapid decay, which is really easy. So the rapid decay cohomology is the fiber at infinity of the perverse realization of the perverse cohomology. And now the big advantage of this perverse realization, this perverse cohomology is the following. You see that in this procedure, everything has been done with 6 functors. So there is, for the rapid decay homology or cohomology, we did topology. So we did cycles and paths and simplices and so on. Here, everything is in terms of 6 functors. So the direct image, the exceptional image, then for the additive convolution, this is also a 6 functors operation, and the sheaf E0 is also something that you can express by 6 functors. So this shows you that whenever you have any other 6 functors context, you can just do the same thing, just copy the formulas. So for example, if you like Hodge theory, well, there is a 6 functors formalism for Hodge modules, and so you get a Hodge theory for X, Y, and F. And it's really just the same formulas. Instead, now you interpret the constant sheaf as the constant Hodge module, and the pull back and push forward as pull back and push forward of Hodge modules. Or if you like L-adic sheaves, well, just write an L everywhere and you get an L-adic theory. So now you should be convinced that there are a lot of cohomology theories for varieties with a function. Good. So that begs the question whether there is one which is universal, better than all the others. I summarize this like this. So for now, we have a bunch of cohomology theories. Each of them takes values in some abelian tensor category, in some tannakian category. So rapid decay cohomology takes values in Q vector spaces. The RAM goes to K vector spaces. The perverse cohomology goes to perv 0. And then there's other cohomology theories that I don't know where they go. And the idea would be to find some guy such that every other cohomology theory factors through the one. So some universal cohomology theory, and it would take values in some abelian possibly tannakian category, which we, if it exists, call exponential motives. So that once you know the exponential motive associated with x, y, f, and cohomological degree n, then you can get out of this motive all the other cohomologies of x, y, f, and n, those which we already know and those which we don't yet know. So there should be a universal property like this. The arrow, well, that's what we would call the motive associated with x, y, and f in cohomological degree n. The functors that you have from exponential motives to the other categories, these would then be called realization functors. That is standard terminology in the idea of a circle of ideas about motives. So exponential motives, there should be some sort of universal cohomology theory for x, y, and f. So in particular, for every algebraic variety, x, subvariety y, regular function f, and integer n, I should be able to associate a motive, which I just call hn x, y, f. And out of this motive, whatever it is, I don't know yet what the category mxk is. Out of this motive, I should be able to reconstruct the rapid decay, the Dirac, the Perverse, and every other cohomology theory of x, y, and f. Now, I will add one more player into the game, which is an integer I called the Tay twist. If you know, you know. If you have never heard about the Tay twist, just ignore this integer. Good. First theorem. Well, such a theory of motives does exist. So there's a Q-linear tannakian category of exponential motives satisfying the universal property I showed before, and this category of exponential motives contains the classical ones. For the classical motives, there is a nice reference. It's a book that came out a few years ago by Annette Huber and Stefan Miller-Stach, something called like Nori motives and periods. So here's the situation. There is this category of exponential motives over K. It contains objects, among others, of the shape h and x, y, f twist I. And inside this category of exponential motives, there is a subcategory spanned by those where the function, those motives where the function f is 0, where the Dirac realization is the classical one, the singular realization is the classical one, and so forth. So you have this category and the subcategory. One should be careful, however. It's not that just because you present a motive with a function f which is non-zero, that it's automatically not a classical motive. So there can be isomorphisms in the category mx between motives where the function is non-zero and the same motive where the function is presented in a way such that the function is 0. So here's, just to get this out of the way, an example. So that the motive h2 of the affine plane together with the function x squared minus y squared, it's actually as a motive isomorphic to h2 of P1. So still, we can say which exponential motives are classical. And that's again where the perverse realization comes in. If you take a classical motive, look at it as an exponential one, and then take its perverse realization, you will actually find a trivial object in the category perv0. So one with trivial fundamental group. And in fact, the converse is true. So an exponential motive is classical if and only if its perverse realization is trivial. So that's a test you can make. And a bit stronger, you can say that these functors, so the inclusion of the classical motives into the exponential ones and then the perverse realization functor, they induce a sequence of tannakian fundamental groups. And this sequence is in fact exact. So you see exponential motives, it's really the perfect mix between, well, perverse sheaves and classical motives. Mind, however, that the first arrow in this exact sequence is not injective, and there is no one on the far left, and it's really not injective. There are many perverse sheaves that do not come in any way from geometry. That being the reason. Okay, let me give you a brief idea of the construction of this category of exponential motives. It goes back to Madhav Nori, who used this same procedure to construct a category of classical mixed motives. And we basically take Nori's construction and amplify it with a function. So I start with, well, a category, let's say, whose objects are these tuples. So x, y, f, and I. And I want to turn these into some abelian tannakian category. And I think of x, y, f, and I already secretly as the motif h, n, x, y, f, and twist I. The problem, however, is that, well, these tuples, they don't even form a nice category at all. I mean, I can look at all these objects. There are some obvious maps, arrows between them that I would like to be morphisms. But my problem is that I don't know yet how to, or will never know how to compose morphisms. See, the problem is that you have kind of morphisms that come from morphisms between varieties, like from x to a variety x prime. And then it should go with the same cohomological degree and with the same tight twist. So these morphisms will never change the value of n or I. However, there should be other morphisms, like when you have a variety x, a subvariety y, and a subvariety z of y. With this triple, you want to have a long exact sequence, and there should be some morphism that increases the cohomological degree. So that goes from hn of y and z to hn plus 1 of x and y. It's kind of a connecting morphism in a long exact sequence. So you want this morphism too. So you can add it, you can put an arrow in the category just for this, but then how would you compose this kind of artificial arrow with another type of arrow? So forget about categories and replace this with the word quiver. And the quiver here is just another word for a category without the composition law. So there's objects, there's morphisms, there are identities, there's a source and a target of each morphism, and that's it. So it's like an oriented graph, if you want, with, well, points and arrows. The quiver is a collection of arrows. Morphisms, well, I have the objects, morphisms. I will describe them like this. So all the morphisms with target a fixed object x, y, f, and I, they are, as I said, of several types. So first, I will add arrows for morphisms between varieties. So whenever I have a morphism from x to x prime, which sends y to y prime, and which is compatible with the functions f and f prime, I will add a map in the quiver from x prime, y prime, f prime, and I to x, y, f, and I. Okay, first type of morphism. Second type, I also already said, so whenever I have a triple z contained in y contained in x, I will add a morphism in the quiver that increases the cohomological degree by 1. So cohomological degree n minus 1 goes to cohomological degree 1. And I think of this as a connecting morphism in a long exact sequence. And I don't have to say how I compose these morphisms of type A and B. And there's a third class of morphisms I decide to add. I don't write out the formula here, but this is a type of morphism that changes now the value of I and is related to the Kunet isomorphism and twist. Good, so these are the morphisms in the quiver. The objects are given. Fine, now I have my quiver of tuples. It's a category without composition law. Still, what I can do now is I can define a functor from this category to the category of vector spaces. A functor, or in the context, is also called a representation of a quiver. So what will I do? Well, I'm taking x, y, f, and I and send it to the rapid decay cohomology Hn, x, y, f, and I. And well, it's well-defined on morphisms of type A, because that's just functoriality of the cohomology. It's well-defined on morphisms of type B, because I will send those to the connecting morphism in the long exact sequence. And on type C, you have to trust that this goes well with the Kunet formula. So I have the functor. Identities go to identities. Morphisms go to morphisms. I don't care about compositions. And once I have such a functor or representation, I can look at its endomorphisms. So an endomorphism of rho of these functors, this would be to give an endomorphism on, well, on the vector space H and x, y, f, I, such an endomorphism for every x, for every y, for every f, n, and I. And these endomorphisms, they will have to be compatible with the morphisms in the quiver. So they must commute with them for all morphisms in the quiver. That's what is to give an endomorphism of rho. And so this thing, it's a huge pro algebra over Q. It's rather big, but it acts by definition on these vector spaces of rapid decay cohomology. That's just taking the endomorphism and see what it does on this particular object. And the definition is now immediate. So we will call an exponential motive just a finite dimensional vector space together with a continuous action of this algebra. That's it. It's obviously an abelian category. It has a forgetful functor to vector spaces, which is exact. So motives, can think of them as vector spaces plus some extra structure. The extra structure is the action of n rho. Moreover, there are the motives H, N, X, Y, F, and I. Well, I just gave them to you. So there's this vector space H and rapid decay X, Y, F, and I, together with the canonical action of the endomorphisms of rho. This is the motive. And I will call it from now on H and X, Y, F, and I. And Norris' theorem is that, well, this construction that made out, I mean, you can do this with any quiver and any quiver representation. Out of this, you make an abelian category, and it will have the universal property you want. The kind of non-formal part here is the tensor structure. So this algebra and rho, it comes with a co-multiplication that makes it into a Hopf algebra. It's co-commutative, but not commutative. This co-multiplication is induced by the Kunet isomorphisms, and it gives you the tensor structure on the category of and rho modules. That means on the category of motives. And this last part, the co-multiplication, this is slightly non-formal, but I mean, that was solved by Norrie essentially, and we needed to adapt this to the context with the function in play. Okay, so here's what we have. We now have a tannakian Q-linear category, which we call exponential motives. So we can take some exponential motive, for example, but not necessarily one directly given by the cohomology of a variety and the function. And then let's say V is its underlying vector space. I want to give it another name. And since now exponential motives are a tannakian category, every object, and in particular M, has a tannakian fundamental group. This group is a linear algebraic subgroup of GLV. So if V has dimension n, this is a linear algebraic subgroup of GLN. And this group is really an interesting invariant of M, and it can tell you, even just as an abstract group, a lot about M. And what is slightly surprising, maybe if you've never seen such a thing, that these groups, they can actually be computed in concrete situation. Even if this looks a bit abstract now, we can compute in concrete examples, in concrete situations, these tannakian fundamental groups, and you will see they are pretty interesting objects. So let's go to an example and show. I want to show you how this works. So this time I'm changing. So now my variety is GM. So that's the affine line with the origin removed. I'm taking a subvariety, just the point 1. And my function is a linear function. F of x is a times x for some scalar a in the field, non-zero. And then I'm looking at the motif h1 of x, y, and f. So let's look at the rapid decay homology first. So the geometrical situation looks a bit like this. So here's my complex plane. I have the 0 removed. So that's why there's a black hole at 0. I have the point 1 marked. And then I have also indicated the region where the function f has a large real part. Now, that depends, of course, on what the scalar a is. But if you pretend for a moment that a is some positive real number in the field k, then that's how it looks like. Otherwise, the region where the real part of f is large, it will be in some other direction, depending on the scalar a. And so if you stare at this picture, you will see 2 cycles. One is the standard cycle around 0. And the other cycle is, say, a path that goes from 1 to, here in the picture, infinity, to from 1 to the region where the real part of f is large. And this is a basis of cycles for rapid decay homology. The dual would be the rapid decay cohomology. So you can already see that the motif M is 2-dimensional. So its underlying vector space is 2-dimensional. And the fundamental group, therefore, is some subgroup of GL2. We don't know which yet, but there are not so many subgroups of GL2. So the list is pretty short. Now, what you observe is that this motif M, it sits in a short exact sequence. And this short exact sequence is, in fact, a long exact sequence. Namely, I'm looking here at the triple empty set contained in Y and Y contained in X. That's a triple of varieties, and it induces a long exact sequence of cohomology, except that in this case, because all the dimensions are pretty small, in this case, the long exact sequence just degenerates to a short exact one. You have M in the middle, and you have a 1-dimensional sub-object and a 1-dimensional quotient. So let's give these objects names. You will see why I name them like this. So the sub-objects, I call it E of minus A, you will see. And the quotient is Q of minus 1. So Q of minus 1 here is the classical motif Q of minus 1, which is like the H1 of GM or the H2 of P1. So the existence, just the existence of this short exact sequence shows you that the fundamental group is a block, well, in this case, just an upper triangular group, because the action of the fundamental group on the vector space underlying M has to respect this short exact sequence. So there will be a fixed space of dimension 1, which is this subspace I call E of minus A. And so the matrix, at least expressed in a convenient basis, the fundamental group will be a block, so group of upper triangular matrices. On the diagonal, you will see the fundamental groups of E of minus A up left and of Q of minus 1 down right. And these fundamental groups, they are both as big as they can be, so they're both GMs. For Q of minus 1, that's well known. And for E of minus A, that's something that you can see, for example, by looking at maybe the perverse realization of this. So see this E of minus A, the motif is just, well, it's the H0 of a point, and on the point I'm taking the constant function A. And if you tensor E of minus A and E of minus P together, what you will get is E of minus A minus B. And so no tensor power of E of minus A is actually going to be the neutral object. So this shows you that the fundamental group of this E of minus A is also GM. So it looks like now something on the diagonal, and we don't know yet what is up in the corner. But then we look really now at the perverse realization of this motif M. It has two singularities, one at 0, one at A. The one at 0 comes from the cube minus 1. The singularity at A comes from the E of minus A. And the monodromy of the local system outside these singularities is really not trivial around 0, which means that this short exact sequence does not split. It does not split as a sequence of motifs because it does not split as a sequence of perverse sheaves. So therefore, the last entry in the fundamental group can also be what it wants. And we get a fundamental group here of dimension 3. It's all upper triangular matrices. And we have computed one. Let's compute, since we are here, let's compute the periods of this motif as well. So a basis for the RAM cohomology is the differential form 1 over x dx and d1. So here d1, for me, this stands for the Dirac charge at 1. And let's integrate. So first thing, I'm going to integrate d1 along the path from 1 to infinity. So to integrate this stupid Dirac charge means just I'm taking the value at 1. So I'm taking the value of e to the minus f at 1, which is e to the minus a. So my first period is e to the minus a. And that's why I also named this motif capital E to the minus a. It's the one-dimensional motif with period exponential of minus a. So next, I'm integrating the Dirac charge around the circle, but this will give 0 because the circle doesn't meet 1. So there's disjoint support. This integral is 0. Now the actual integrals. 1 over x dx integrated along the circle. This is Cauchy's formula. It gives you 2 pi I. And the interesting one now is to integrate 1 over x dx from 1 to infinity, but in the integral, you write also exponential of minus ax. That's the last integral. And the students will be shocked sometimes that they cannot compute such a thing. In fact, this integral, it does not have an expression in elementary, let's say, trigonometric functions. So this is what's called the exponential integral function. So the best thing you can do is just you can give it a name, and the last period would be exponential integral function evaluated at 1. So this is the full period matrix of the motif. And you observe now that this period matrix and the fundamental group kind of look similar. And this is, of course, also not an accident. So first, the existence of the short exact sequence is exactly what produces the 0 in the fundamental group. And it's also the same thing that produces the 0 in the period matrix. So that is maybe not such a surprise. But then the other 3 entries in the fundamental group, they can be chosen freely. So there's 2 copies of GM and an additive copy. And in the period matrix, it also looks like these 3 numbers that you get are kind of unrelated to each other. And there's not one which would be a rational multiple of another one also. And you can make this a conjecture here that such a thing is really true. So let's take an exponential motif, just any, with underlying vector space. Let's look at the fundamental group. And then let's look at the algebra generated by the periods of M. I mean, the algebra generated by the entries of a period matrix of M. Such matrices we have just computed. And the conjecture would be that, at least numerically, the dimension of G would be the same thing as the transcendence degree of this algebra. So in the example before, we had 3 non-zero periods, e to the minus a, exponential integral of a and 2 pi I. And the period conjecture here would say that these 3 numbers are algebraically independent. Well, to finish off, I think I have time for one more example. Let's look for once at a higher dimensional one. So this time my variety is A2, the affine plane. My subvariety y is the unit square, and the function is the product of coordinates. So here is the picture, but it's the real picture. So this is a plane. It's not the C plane, it's the R2 plane. I'm marking, so the unit square, it means I mark the lines x0, x equals 1, y equals 0, y equals 1. This is my unit square. And I've drawn you the line x times y is equal to r, and it intersects also in a complex world, the 2 lines x equals 1 and y equals 1. Okay. For rapid decay cohomology, you immediately see 2 cycles in the picture, which is the square and the triangle. And there is one more cycle, which is kind of hard to see because it's just the real picture of something in a complex world. This red line, so it's the locus x times y is equal to r, but in the complex world, this is actually a C star. Right? So x can be any non-zero complex number, and y is r over x. So the red line is actually C minus the origin, so it's topologically a circle. And the last topological cycle that you have here is a disk whose boundary is the standard circle in the C star. So that's, if you glue a cell like this, you get another homology class. So the motif H2 x, y, f is actually 3-dimensional. So you have the square, the triangle, and the disk. What I want to do now is I'm not really interested in the square and the triangle individually, so I will pretend that the intersection at the point 1, 1 does not happen. And to pretend is actually something that we can really do. So we blow up the affine plane in this point. This separates the 2 lines. And the motif I'm actually looking at is not the H2 of x, y, and f, but it's the image under the blow-up map of this H2, y, and f. And what happens now is that the square and the triangles cycle don't exist individually anymore, but their difference does. Right? So I have removed the intersection at 1, 1. All right. So now this M is 2-dimensional. I can write differential forms. So one is dx dy. The other interesting one is the Dirac charge at 0. This is at the RAM basis. And so the fundamental group, again, because it's a 2-dimensional motif, it's some subgroup of GL2. Now, kind of same game as before. You look at long exact sequences associated with various inclusions of the subspaces, and you find that this motif M is again an extension, this time of the classical Q twist -1 by the classical Q twist 0. So we have here an exponential motif, which is an extension, a non-classical extension of classical motifs. And it's really an exponential motif and not a classical one. So from this short exact sequence, you immediately see that the fundamental group is upper triangular. There's a 1 in the upper left corner because Q of 0 is the neutral object, and Q of -1 has fundamental group GM, so there can be anything in the lower right corner. And in the extension, well, you don't know, but depends whether this sequence is now split or not. Well, it's not split. And this is, again, something you see on the perverse realization. So there is one singularity this time, and there is non-trivial unipotent monodromy around this singularity, and this shows you that there is no splitting of associated perverse sheaves, so there is no splitting of motifs. So the fundamental group is this time 2-dimensional, and it's this group here. Good. So the periods, easy this time. So there is a 1, a 0, and the 2 pi I. The 1 is the period of the Q0. The 2 pi I is the period of minus Q of minus 1. The 0 is, well, because there has to be. And so there's the one period, interesting period left, and it's given by the integral over the difference of these two cycles, exponential minus xy dx dy. So let's go to somewhere aside, compute this integral. So write just out what it is, integral 0, 1, 0, 1, exponential minus xy dx dy, compute it. Integral 1 infinity, 1 infinity. This is over the triangle exponential minus xy dx dy. Make a change of variables, call z, instead of x, write x over y, write it out, and you will find a very well-known integral expression for the Euler-Mascheroni constant, little gamma. So that's our answer. This integral is the Euler-Mascheroni constant. It goes in the period matrix, and the conjecture would now state that the transcendence degree of the algebra generated by 2 pi I and gamma is 2. So it's kind of a folklore conjecture that gamma is an irrational or even transcendental number. Here there is now some real motivation. Why? Well, it's still a conjecture, and we don't prove any transcendence statements. But here is some kind of better motivation, except better than I didn't find anything on Wikipedia. So, and I think this is a good place to stop.
Thank you, Peter. Let's thank Peter. Any questions, anyone?
Payman, is there a time for a quick question?
I think so. Yeah, I have quite a few questions too. Yeah, go ahead.
Yeah, I mean, a lot of questions. But firstly, to your last comment about not proving anything, the point is realizing gamma as a period in any definition of the word is already very interesting, because it doesn't appear in the Zagier-Kontsevich concept of a period. You know?
No, it does not.
So
and it should not. So this motive we just discussed about, it is not a classical one. And so its fundamental group is always larger than, I mean, you take this motif and you take any direct sum with a classical motif, the fundamental group will always be larger. Right? You take any classical motif M and you make the direct sum with the motif for gamma, because of the perverse realization, you will always get a bigger fundamental group. So the conjecture would even state that little gamma is transcendental over the field of all classical periods. And so, yeah, it should not, I mean, there could always be an accident, but it should not appear as a classical period in any way.
And even though that last sequence that you wrote down looked like a mixed state motive, it's not a mixed state motive, right?
Yeah, it is, but it depends. So it's a mixed state motive in the category of exponential motives. So it is. So in the for classical mixed state motives, what you have is that when you have this extension Q of minus n by Q, and these extensions are given by K theory, right? And the periods of these extensions are zeta values. So, for example, the extension of Q twist minus 3 by Q, this is you can do a nice one classical, and the period in the upper right corner is zeta of 3. Now here we have Q of minus 1 extension by Q, and the period, well, it's not zeta of 1,
yeah,
but it's the logarithmic derivative of zeta of 1. So
I see.
It's, yeah, the zeta function has a pole there, and you cannot have the value, but with a little bit of goodwill and flexibility, you get the normalized value of the zeta function at 1.
No, very interesting.
Any other questions? So, I can't see anything in the chat box either. So if no one else has any questions in the meanwhile, I'll ask maybe 1 or 2 questions. So So the subcategory of an exponential motive, if you take the semi-simple skeleton of that, so category of all semi-simple objects, is there like a interpretation, some sort of a, like in the classical thing, this would be the motive, smooth projective?
Yes, so there is a notion of purity, first of weights and therefore of purity. So exponential motives, they do have a weight filtration, and how do you call it, semi-pure. So the pure objects are all semi-simple, and every semi-simple object is a direct sum of pure ones. So there is this mechanism that goes on, yes.
And then I imagine that the category of classical motives, so the subcategory of classical motives would be closed undertaking sub-objects in this larger category.
Yes, yes, it is closed undertaking sub-object. I mean, first all tensor constructions, but also sub-objects and quotients. So otherwise, you would not have this short exact sequence of fundamental groups.
Right. Yeah. I see.
And so that's something. Yeah. So, but it's not stable. Interestingly enough, it's not stable under extensions.
Yeah.
Again, my last example.
And then I browsed through the book very quickly. I mean, I read parts of the introduction more carefully, but then browsed through this rest. You said something that, so do you, like in this larger category, do you have a one-dimensional motives of, let's say, weight 1?
So yes, there is a motive Q1/2. And it's very easy. So you take the affine line and you take the function x squared. So what you find as a period is the integral from minus to plus infinity exponential of minus x squared dx. What is the answer? Root of p. So yes, there is, and you can actually show, so the tensor square of this motif is a Q of 1. So it makes sense to call it Q of 1/2.
And then there's probably like a Q of 1/4 too, or no?
No, there is no. There's Q of 1/2, but it's, so what you have rather is motifs that give you special values of the gamma function.
Yep.
So gamma of 1/2, fine, but then gamma of 1/n, you have them too, but the motif that produces gamma of 1/n and 2/n and all its little companions, it's a motif of dimension n-1. So I showed you the one with the fourths of gamma, right? So this is the affine line with the polynomial x to the power 4, and it produces for you gamma values, gamma 1/4, gamma 2/4, and gamma 3/4, together with some algebraic noise that is not too much important. And well, there is a transcendence conjecture about special values of the gamma function, which is to Lang and Rohrlich. And well, it's just what the period conjecture says about these particular motifs.
Very interesting. Very interesting. Anyone else has any questions?
May I ask a question?
Yeah, please go.
So in the very beginning, we assume that x may not be integral, so it may not be irreducible. But in all the examples presented later, x are all irreducible. So my question is, why do we specify that we do not require x to be irreducible?
No, so x is reduced. X is reduced, so it doesn't have. It doesn't have multiplicities, but it's not necessarily irreducible. So the x can have several components. Maybe see my variety y somewhere in the unit square. Well, it's a union of 4 lines, right? So it's.
I see.
Maybe you just confuse the word reduced and irreducible.
Yeah, that's yeah.
No. It's just see, it's really very flexible. So varieties, they can have components. They can have like like unions of curves, disjoint or not disjoint. That's all allowed. And it's pretty important that you have this flexibility. but you really want varieties and not schemes. So you don't want a I don't know, spec of k of x modulo x to the power 5.
Yeah, may I ask a copy of the slides?
Of course, of course.
I think the slides, I mean, if Peter agrees, probably they're going to be posted on the Fields webpage.
Yeah, let's agree.
Thank you very much.
Okay. So we don't want to take too much more time of Peter. Thank you so much for a great talk, and we'll thank Peter again.
Yeah, thank you. Thank you. If you have a question tomorrow, write me an email.
you have a couple of 100 questions tomorrow. You can...
Yeah, I actually have a long list of questions.
Yeah, no, yeah, feel free. Always love a good question.
Great.
Thank you.
Thanks.
And next week we have, I think, Cristiana Bertolin.
Okay, good.
Yeah.
Is Christian? Cool.
Yeah. Okay. Thank you.
Bye.
Yeah.
Bye-bye.